Welcome to this session on CCNA tutorial, Network Fundamentals. This video is aligned with Cisco's official CCNA 200-301 exam blueprint and is designed to guide you step-by-step toward certification success. In this lesson, we cover Section 111, Wireless Principles. We'll discuss and explore the core principles that make wireless networking work. We'll start by looking at how Wi-Fi uses radio frequencies and how antennas, obstacles, and RF behaviors influence signal quality. Then we'll break down the different wireless bands, channel structures, and regulatory considerations that affect real-world deployments. We'll also look at WLAN design models, including autonomous, lightweight, and cloud-managed architectures, along with AP operating modes like Local Mode and FlexConnect. Finally, we'll explore AP and WLC management concepts and review the security protocols that protect wireless networks. By the end of this section, you'll have a solid understanding of how Wi-Fi functions from the RF layer all the way up to authentication and encryption. Wireless networking lets devices communicate without physical cables by using radio waves. The technology is built on IEEE 802.11 standards, which define how Wi-Fi operates across different frequency bands. With wireless, users gain the flexibility to move around while staying connected, and businesses reduce the amount of cabling required. The goal is to deliver reliable network access with mobility, convenience, and cost efficiency. Wireless technologies are organized by how much area they cover. WPANs handle very short distances, such as your Bluetooth headset. WLANs extend a local network across a building using Wi-Fi access points, and WMANs stretch connectivity across a city or between buildings using outdoor wireless links. Understanding these categories helps you choose the right technology for the right distance and use case. A wireless personal area network is designed for communication within just a few meters. It relies on technologies like Bluetooth, NFC, and Wi-Fi Direct to connect personal devices such as headsets, printers, and keyboards. These technologies often replace short cables, and they commonly operate in the 2.4 GHz ISM band. WPANs are ideal for simple, low-power, close-range connections. A wireless LAN provides network access across medium distances such as offices, classrooms, and homes. Built on IEEE 802.11 Wi-Fi standards, it uses access points connected to a wired backbone to extend the LAN. WLANs allow laptops, phones, and IoT devices to stay mobile without losing connectivity. In enterprise networks, WLAN controllers and lightweight access points manage Wi-Fi centrally for consistency and reliability. A wireless metropolitan area network connects locations across wide areas such as cities or large campuses. These links often use point-to-point or point-to-multipoint antennas to bridge buildings where cabling isn't practical. Organizations choose WMAN technologies to connect warehouses, remote buildings, or outdoor spaces at lower cost than laying fiber. It's essentially wireless used as a metropolitan-scale backbone. Wi-Fi communication depends on three radio properties: amplitude, frequency, and wavelength. Amplitude controls signal strength, while frequency determines coverage and how well the signal penetrates walls. Higher frequencies, like 5 or 6 GHz, offer faster speeds but shorter range. Wavelength ties everything together by describing how the wave behaves in the environment. These fundamentals influence how we design wireless networks. When an AP transmits at high power but a client device transmits at low power, a mismatch occurs. The client may hear the AP clearly, while the AP barely receives the client, causing unstable connectivity. Beyond power levels, coverage is also affected by antenna type, walls, noise, and even humidity. These factors explain why signal bars don't always tell the full story about connection quality. Antenna design influences how Wi-Fi signals spread. Omnidirectional antennas provide 360-degree coverage and are ideal for general indoor use. Directional antennas focus energy in one direction, making them perfect for long-distance links. Patch and panel antennas offer controlled coverage in hallways or rooms. Understanding antenna patterns helps ensure coverage where users actually are. Radio signals behave differently based on what they encounter. Walls and dense materials absorb RF energy, reducing signal strength. Smooth surfaces like metal cause reflections and multipath, which can distort the signal. Refraction bends signals when they pass through materials like glass or liquids. These behaviors explain why wireless performance can vary dramatically from room to room. The 2.4 GHz band is crowded, not just with Wi-Fi devices, but with many household appliances. Microwave ovens, baby monitors, RF cameras, and even fluorescent lighting can disrupt Wi-Fi signals. Because these devices don't follow Wi-Fi rules, their interference can be severe and unpredictable. Knowing these sources helps you troubleshoot issues that appear random, but are caused by non-Wi-Fi transmitters. Wi-Fi operates in unlicensed spectrum, meaning many devices share the same airspace. When too many devices compete, signals overlap and cause collisions, similar to traffic congestion. This is why careful channel planning is essential, especially in busy environments. Understanding how shared frequencies work helps explain why performance drops when the spectrum is crowded. Wireless standards are defined by IEEE, but power limits and frequency access are regulated by FCC, ETSI, and other regional bodies. These rules prevent interference and ensure devices operate safely. Depending on your country, some Wi-Fi channels may be restricted or require additional measures like DFS. Always consider regulatory requirements when designing or deploying wireless networks. Here, we're looking at how Wi-Fi has evolved across the different 802.11 standards. The very early versions, like 802.11b and G, ran only in the 2.4 GHz band and offered relatively slow speeds. Then, 802.11a introduced 5 GHz, which gave us a cleaner spectrum but slightly shorter range. With 802.11n, we finally got dual-band support and a big jump in performance thanks to MIMO. From there, 802.11ac focused entirely on 5 GHz and pushed Wi-Fi into the gigabit era. And the latest version, 802.11ax, also known as Wi-Fi 6, brings major efficiency improvements, with Wi-Fi 6E extending those benefits into the new 6 GHz band for even more capacity. Each Wi-Fi generation, from 802.11b to 802.11ax, improves speed, efficiency, and reliability. Lower frequencies like 2.4 GHz travel farther but suffer more interference, while higher bands like 6 GHz offer clean spectrum with shorter range. Measurements such as RSSI and SNR help us assess signal quality, and factors like walls, placement, and antenna type influence overall performance. The 2.4 GHz band provides long-range, wall-friendly coverage, but is crowded and limited to 3 non-overlapping channels. Because channels overlap heavily, wide channels like 40 MHz are not recommended. This band works best for low-bandwidth devices, sensors, and older clients. Its strength is coverage, but capacity and interference are major limitations. The 5 GHz band offers more channels, cleaner spectrum, and support for wide channels such as 40 and 80 MHz. This makes it ideal for high-throughput applications and dense office environments. Some parts of the band require DFS to avoid radar systems, which may cause channel changes. Although the range is shorter than 2.4 GHz, performance and reliability are significantly better. The 6 GHz band, introduced with Wi-Fi 6E, provides an entirely new, clean spectrum free from legacy devices. It supports many non-overlapping channels and wide channels up to 160 MHz for multi-gigabit speeds. Only Wi-Fi 6E devices can use it, which reduces interference. The trade-off is shorter range and more sensitivity to obstacles, but the performance benefits are huge. Different WLAN modes define how devices communicate. Ad hoc mode enables direct client-to-client links, but does not scale. Wi-Fi Direct improves this by adding security and service support. Infrastructure mode, the most common approach, uses APs to coordinate access and roaming. Mesh networks extend coverage without cables, and workgroup bridges connect wired devices to wireless networks. WLAN architectures vary in how they handle configuration, security, and control, and each model fits different deployment sizes and requirements. We'll compare autonomous access points, controller-based lightweight APIs, and modern cloud-managed solutions to understand how each approach delivers wireless connectivity. An autonomous AP operates entirely on its own and performs all Wi-Fi functions locally. It manages authentication, encryption, channel selection, and WLAN mappings without a controller. This model is easy to deploy but hard to manage at scale, since each AP must be configured individually. It suits small environments with just a few access points. A lightweight AP relies on a central wireless LAN controller to manage configuration, security, and RF optimization. The AP handles real-time tasks, while the WLC controls policies and channel/power decisions. This model enables fast roaming, consistent configuration, and easy management across many APs. It is the default choice for medium to large enterprise deployments. Cloud-managed APs store configuration and monitoring data in the cloud instead of an on-site controller. They pull their settings automatically once online, making deployment extremely simple. The cloud dashboard offers real-time visibility and centralized control across distributed locations. Traffic typically stays local, while only management traffic reaches the cloud. This approach is ideal for retail, schools, and branch networks. In local mode, all client traffic is tunneled back to the WLAN controller, allowing centralized policy enforcement and consistent security. FlexConnect mode is designed for branch sites, where the AP can switch traffic locally and continue operating even if the WAN link to the controller fails. The choice of mode depends on network topology, WAN reliability, and desired control level. The SSID is the wireless network name that users connect to. APs broadcast SSIDs in beacon frames and can host multiple SSIDs mapped to different VLANs. Using meaningful names helps users select the right network, while WLAN mapping separates traffic for corporate, guest, or IoT devices. Hidden SSIDs provide no real security and can even create additional risks. When an AP joins a controller, it must discover it first. DHCP option 43 can point the AP to the correct WLC IP address, while DNS discovery provides a fallback using a predefined hostname. Accurate time is also critical. If the WLC and AP clocks differ, certificate validation may fail, preventing the AP from joining. These mechanisms ensure smooth AP onboarding. Wireless security begins with authentication and encryption. Authentication verifies who is connecting, using passwords, certificates, or tokens. Encryption protects data as it travels over the air. Legacy methods like WEP and TKIP are insecure, while modern networks rely on AES-CCMP for confidentiality. These fundamentals form the basis of secure Wi-Fi. WPA and WPA2 introduced major improvements in wireless security. WPA used TKIP as a security patch, but WPA2 established AES-CCMP as the industry standard. Both support personal mode with a pre-shared key and enterprise mode with 802.1x authentication. WPA2 remains widely deployed and provides strong security when paired with complex passwords or radius-based authentication. WPA3 enhances wireless security by improving authentication and adding protection against modern attack methods. Personal networks use SAE, which prevents offline password cracking. Enterprise networks gain mandatory protected management frames and optional 192-bit encryption. WPA3 also improves public Wi-Fi through OWE and introduces DPP for secure IoT onboarding. These upgrades make WPA3 far more resilient. Open networks allow users to connect without a password, but traditionally this meant no encryption at all. With WPA3, OWE adds automatic encryption, so each client gets a unique key, preventing other users on the same network from eavesdropping. It still doesn't authenticate the user, but it protects the data in transit in places like cafes and airports. For IoT devices, DPP simplifies secure onboarding by using QR codes or NFC to deliver credentials out of band, making enrollment easier and more secure. 802.1x provides enterprise-grade access control by integrating Wi-Fi with AAA services. When a client connects, the AP or WLC acts as the authenticator and forwards credentials to a radius server. The server validates the user and assigns appropriate permissions, generating unique encryption keys per session. Compared to PSK, 802.1x offers stronger security, better scalability, and identity-based access. Best practices for securing Wi-Fi focus on using strong encryption and modern authentication. WPA2 with AES is the absolute minimum, and WPA3 should be used whenever possible. Avoid outdated methods like WEP or TKIP as they are easily broken. Combining strong encryption with 802.1x authentication and proper key management provides a robust security foundation. Wireless networks must be designed with RF fundamentals, channel planning, and security in mind. Modern bands like 5 and 6 GHz improve performance, while AP architecture and management tools simplify deployment. Strong security, through WPA2 or WPA3, AES encryption, and 802.1x authentication, protects users and data. Before moving on, take a quiz to test your understanding. Quizzes, summaries, and slides are available on ccna.academy. If you have any questions, leave a comment below and I'll be happy to help. Up next, Section 1.12, Virtualization Fundamentals, where we'll look at how virtualization works, why it matters, and how technologies like VMs, containers, and VRFs help optimize network resources.